The Robot Explorers, our envoys in the solar system. They reconnoiter where we want to go and where we'll never go. Liftoff for Mars, a destination top of our visiting list. Thrust clear of Earth's atmosphere on a Delta rocket, this American mission to the Red Planet is a robotic trailblazer. Stage by stage, like an insect emerging from a chrysalis, this planetary scout sheds nose cone and propulsion units. Soon, it flies free. As Earth recedes, a single wing unfurls. It's the solar panel, the energy source that powers the craft and its signals to mission control. For this is the Mars Surveyor Orbiter. As the name implies, its task is to slip into Martian orbit and survey the planet as never before. On the far side of Mars, a retro rocket cuts Surveyor's speed. Orbital insertion is successful. But the orbit is elliptical, sweeping far into space. Surveyor needs a circular orbit. The key is the solar panel. At closest approach, the panel becomes an aerobrake in the Martian upper atmosphere. Only with a circular orbit can Surveyor properly survey. Swing by swing, aerobraking does the trick. Surveyor Orbiter is to study weather and terrain. A companion craft is to operate on the surface. It's a 10-year program. Launches are planned every 26 months. It means that when we arrive, there'll be a book, The Surveyor Guide to Mars. Voyager, most famous of the robots, the mission that shows us Jupiter. Twin craft, Voyager 1 and Voyager 2 send us mouth-watering images. Launched in 1977, the probes careen through the gas giants. Saturn and its remarkable rings, ringlets in close-up, and this astonishing approach by Voyager 1. Saturn is the climax for Voyager 1. Mission complete, it exits the solar system. Voyager 2 heads for the outer giants. 5 years later, Uranus. And its craggy little moon, Miranda. This Miranda animation is from Voyager data. At this vast distance from the Sun, Voyager relies on nuclear rather than solar energy. 1989, Neptune, last of the giants. Voyager has been 12 years in space. Some time-lapse of the South Pole. An arc over the North Pole, and Voyager is done. An American triumph. Voyager 2 heads for interstellar space. Like its sibling Voyager 1, lost forever from the planets. Launching from Space Shuttle in 1990, this robot targets the Sun. But the route is via Jupiter. There, with gravity assist, the craft is catapulted toward the Sun. The mission is called Ulysses. The aim is to fly directly over the solar poles. Ulysses does it, and research moves on. In 1989, another robot launched from shuttle Galileo. It's headed for Jupiter, but Galileo is short on thrust. Gravity assist is the answer, once round Venus and twice by Earth. It takes 6 long years, but it's worth it. This mission, to drop a probe into the merciless atmosphere of Jupiter, is only for a robot. At a command from Earth, the probe deploys. It's a descent into hell. The deeper, the denser, the hotter. There are terrible winds. But the probe keeps transmitting. Data is flashed to the mother craft for relay to Earth. The atmosphere is a poisonous soup, so dense that after an hour, the probe is crushed. Up above, Galileo slots into orbit. A gigantic ellipse, but slingshotting with a purpose. Each loop, a chance to photograph the 4 largest moons of Jupiter. Galileo's flybys yield dramatic pictures. July the 4th, 1997. America celebrates Independence Day with a night landing on Mars. It's a bouncing robot, the spunkiest vehicle ever to hit the red planet, Mars Pathfinder. It comes to rest on an ancient floodplain. Cocooned within, technology that beams us 16,500 images and more than 2.5 billion bits of information. But first, the deflation of the protective bags. Then, like a flower, Pathfinder spreads its petals. Sunrise, solar power, and contact with Earth. And so to work. Pathfinder has stereo cameras. A color image is produced by passing light from a lens through 3 filters. The process is duplicated with light from a second lens. So there are 2 images of the same scene. When merged, we see the Pathfinder landing site in 3D. A site worth investigating. Cue the rover. Although controlled from Earth, the rover can steer itself. Batteries last so well, the mission goes 4 times longer than planned. The only mishap, some bad driving. The first Martian fender bender. Elsewhere, there are worse mishaps. This Ariane rocket, carrying 4 robot probes, never makes it to orbit. Nor do these darts from Russia. Rocket failure means they never leave Earth orbit. They were supposed to analyze Martian soil and transmit the results to an orbiter. The great dishes that talk to our robots are the boon of space exploration. Through them, without leaving the security of planet Earth, we map and catalogue new worlds. Had Christopher Columbus been so lucky. Future Shuttle. It takes off as a plane and it climbs. With sufficient height and the right speed, the pilot engages the rocket engine. Future Shuttle is in space. Airport to orbit in one smooth hop. At the leisure wheel in the sky, it's Friday night. Future Shuttle is bang on time. Less than half an hour from takeoff, another party docks in and checks in for a weekend in space. A break to watch the heavens above and the Earth below. But this wheel is much more than a resort. It's a spaceport, a staging post for onward journeys to the moon. For the moon is colonized, and for economy's sake, it's more efficient to ferry cargo and personnel from Earth orbit than directly from Earth. In gravity 1/6 of hours, the transporter pod coasts to touchdown. This is no campsite. It's a metropolis. People live and work here. Scientists, miners, gardeners. And beyond, on Mars, more colonies. Sealed, self-contained cities, modelled on the lunar bases and serviced by them. The moon and those spaceports are our stepping stones to the planets. That's the fantasy. This is the reality. ISS, the International Space Station. Assembled in Earth orbit around a Russian core, components are from America, Canada, Europe and Japan. Completion is scheduled for 2004. Shared by 13 nations, there are multinational crews and robots like this, an inspection ball. It monitors astronauts on spacewalks and checks the superstructure. Robot arms reposition modules. Every technology to maintain a structure the size of a football field. Initially, crews travel aloft on the old space shuttle, their lifeboat, Soyuz, the ferry used by the Russian space station Mir. 6 to a crew, lots of room with tours of duty just 90 days. Life on ISS is congenial, luxury compared with Mir. ISS is costing $100 billion. It takes over where Mir leaves off. The main objective, to test the long-term effects of living in space, vital if we're to get to Mars. And this is the new shuttle. Or at least a half-size prototype, the X-33. As construction of the International Space Station begins, so do test flights of the X-33. It's the forerunner of VentureStar, the shuttle that'll lift cargo 20 tons at a time to ISS, and it'll do it 10 times more cheaply than the old shuttle. And unlike the old shuttle, which dumped fuel tank and boosters on every flight, Venture Star is all-in-one, entirely reusable. From Earth orbit, a rocket to Mars. It's the late 21st century. Thanks to spaceports like ISS, the Red Planet is now colonized. The rocket shed, we close with this cold little world and its wispy atmosphere. Millions of kilometers from home, a city of human beings. But it's life in a bubble. Airtight corridors connect labs, factories, offices, homes. Outside with no spacesuit, you're dead. This city is self-sustaining. Biospheres produce food, energy is solar-powered, everything is recycled. Rocket packs are fun, but to be free of pressure suits, couldn't we turn Mars into Earth? Possibly, but it would take 100,000 years to induce a greenhouse effect and breathable air. To travel beyond Mars from the spaceport of the future, it would take up to 15 years to reach Pluto, the outermost planet. We're held back by our propulsion systems and limited fuel capacity. Solar energy can help, but on a voyage through the outer planets, it's a diminishing resource. The farther we journey, the dimmer is the light of the sun. But there's still the solar wind. We might gather it in vast sails and drift outward on electrified particles blown from the sun. Beyond the solar system, we need new propellants. Even at 1/10 the speed of light, it would take us 40 years to reach the nearest star. Ion or nuclear propulsion might give us the thrust, but for the time being, such voyages are science fiction. So where next? The Moon and Mars are first on our list, but what about Venus, Earth's hot sister? Might we colonize this hellish planet, disperse its clouds, reverse the runaway greenhouse effect? Maybe. The trick could be to seed the atmosphere with green algae. It feeds on the crushing carbon dioxide and releases oxygen. Water accumulates on the surface, the steamy climate cools, life takes hold. It's no quick fix. Only after hundreds of thousands of years does Venus start to look like Earth. And even if it's possible, is such planetary engineering desirable? Nature has a habit of reasserting itself. But how about this for planetary engineering? It's the idea of space guru Arthur C. Clarke. A tower rises 36,000 kilometers from the surface of Earth. An elevator to orbit. The tower is one of 4, reaching from the equator, the spokes of a gigantic wheel of which Earth is the hub.